Hi everyone, my name is Tim. I'm an engineer based out of Copenhagen, Denmark at a company called Clued In. And I'm wanting to highlight two pieces of technology that have allowed us to really raise the level of precision when it comes to this area of master data management. And one of those key technologies is called Neo4j, which is, it falls within the graph database family. And of course the other being some machine learning techniques. So when we talk to most of our customers and potential customers today, they either fall into kind of two areas. One is that they are right in the middle of their big data era, where they have been taught to kind of, or told from the market to capture every single signal that they have on customers or individuals or signals from IoT. But we also see this kind of generation of companies that are wanting to be much more data-driven, i.e. move into this era of smart data. Now, the reason why platforms like Clued In exist, and we fall into this space of what is called integration platform as a service, is because if you have a look at your companies, every single individual here, well, I'm pretty sure you use anywhere from 30 to sometimes 350 systems to solve things at work, like sending mail and making phone calls and managing customers and analytics and projects and to-do lists and accounting and invoicing, and of course you can imagine the list just goes on and on. And if you have a look at the data integration space today, there are lots of frameworks out there to help us as engineers to pull and wrangle data in from many different sources. However, what we find in the market that there's these manual approaches of downloading potential studios and mapping different systems together is not only laborious, but tedious and costly as well. So Clued In kind of takes a fresh kind of angle on this by trying to integrate data from different systems automatically. And I want to emphasize the word trying in this kind of story I'm going to take you through. So this is part of the stack. This is the stack that drives Clued In. And I want to focus on two areas today. One would be the graph database, and one is the processing layer. And I want to show you how we use this to increase the precision of being able to merge data from discrete, ambiguous systems in a most automatic way as we can. So if we wind back about 6 months ago, I gave a talk in London at a Neo4j event where we showed how we built a decision tree or a decision engine utilizing Neo4j and certain machine learning techniques. And I'm sure, like most people in the room, when we kind of at Clued In entered the kind of machine learning space and kind of saw these new engineering techniques that we could add on top of the techniques we were already using to build a decision engine, we kind of jumped in early and started to look at the different areas and topics we could focus on to get this kind of level of precision. And so we started out quite small. One of the great things about having a data integration platform is the ability to search across all your data from one single place. You can imagine one thing that would bring quite a lot of value to our customers is to be able to search for people within images. So there are lots of different approaches for this. One of the speakers before actually touched on it, and that was that we used a GPU SDK library called CUDA in combination with a library called Torch to be able to give our customers image object detection. So we started out small, and I'm sorry if this is kind of hard to see, but I placed a picture of myself into this engine that we trained to see what the output was. This is a picture of me at my brother's wedding. And here were the results that it came out with. And to be honest, we were a little bit skeptical, and the skeptics in the room would also say, why didn't that detect glasses? Why didn't it detect male or hair or something like this? And I think you would be very right to be skeptics, because this for me and this for our machine learning team at Clued In sums up some of the machine learning techniques that we're utilizing. So let me give you another example. I mentioned we're out of Copenhagen, Denmark. So when we put the picture of our CTO, Martin, in, that looks like your classic Norwegian, long hair, listens to death metal. It classified him as 97% a fur coat. And I guess what I'm trying, I have no idea where bucket came from. That for me is the biggest surprise, to be honest. And I guess what I'm trying to say is that one of the strengths behind machine learning is that it helps us in the data integration space to only elevate the level of precision. Machine learning, when it comes to data merging, it's not about right or wrong. It's about how can we raise our precision now to a higher perspective using new techniques. And I will change my wording there, combining different techniques. I want to highlight one thing where it comes to the graph database that we use, Neo4j. And that is that context is so important when you're trying to merge data from different systems. Now, if you were looking at our technology stack before, you would have noticed that we have a relational database there. We have a search index store. We have a distributed memory cache. We also had this graph database. Now, if you look at the others, like relational and document stores, one of the things that differentiates a graph database from those stores is that when you write data back to that graph database, it maintains the context, i.e. it knows the data that sits around it. It knows the inferences or the relationships between the data that sits in close or potentially indirect proximity to that data. And if you have a look at the other types of stores, like relational and search stores, sure, you could do this, but you would have to write back so much superfluous information to kind of get close to this type of context that's necessary. I also wanted to highlight three kind of main points about a graph database, just in general. It doesn't need to be Neo4j, it could be any of the graph database stores. They all support this type of design, is that graph databases are fantastic at joining data. They're inherently good at joining across data that could be 100 different joins. So if we could picture a graph or a huge company graph, one node that would exist over in sales and one node that would exist in engineering, the ability for a graph database to reverse engineer the connections between that data, that's just something it was designed to do. The other thing that the graph database is fantastic at is pattern matching. And I don't mean pattern matching like clustering algorithms. It's a different type of pattern matching. And I want to give you an example later. So after finding out that Martin was a fur coat, we found two kind of areas within the machine learning space that allowed us to raise our precision level, and they were clustering and neural networks. And I'll give you some real-life examples of the data that we pushed through it and how we were able to flip our traditional ways of processing data to using these techniques. So in the end, we used the graph database structure. This was the decision engine design that we went up with. This was the fact that we built a recursive decision tree that organically grows, expands, and collapses, then learns. Now let me explain that. If you are trying to figure out from all the different data that you plug in, let's just say it's CRM data, if you are trying to figure out if John Smith and Johnny Smith are actually the same person, what we would do is, what we would do is we would explode out both of those nodes, John Smith and Johnny Smith. And we would not only ask all the other data that sits within the graph, but external sources like in Denmark we have what's called the CVR registry, which is information on companies and board members, and in all around Scandinavia, they have their own systems. In London, there's Company House. So we would combine external systems with internal systems for us to try find out very fuzzy attributes about John Smith and Johnny Smith. Now, of course, something like John Smith is such a common name, right? The great thing is that when we're working in your company's data, well, that's our context, right? We don't have to work in the entire context of the world like something like a search engine does. So I want to highlight 4 techniques that we used that allowed us to gain the biggest precision gains in being able to merge data across different systems. And I'm going to continue with this example of merging individuals. So it's broken up into 4 different categories. The first is pattern matching. And just like I said before, this is not pattern matching like clustering. This is something different. The next was practical. So this was a practical change we made. You could imagine that if we figured out that John Smith and Johnny Smith were actually the same person, can you imagine all the other decisions that we've made in the past that might need to be changed because we now know that fact? We may have not merged, for example, other data within our system because we didn't know John Smith and Johnny Smith were the same person. So how did we handle one merge operation not causing, and this actually happened, the entire graph to be just recursively evaluated? And then finally, the next 2 iterations we made to our merging engine broken up into a supervised and an unsupervised category. So let's go to those in detail. So to understand how we utilized a graph database to pattern match and increase the ability to merge data, first of all, you need to understand the supervised learning approach or addition that we made. So those who are working in the data space, I mean, you've probably heard of all of these different ways of referring to this. Entity reconciliation, entity linkage, deduplication, they're all synonymous. They all mean the same thing. It's the idea of taking data and cleaning it and validating it and potentially merging it. So the way we do this at Clued In is in a very unsophisticated manner, is that we have classic crawler systems that go out and fetch data from Salesforce, Dynamics, Twitter, whatever the data sources that you kind of plug in. Now, each of the individual entities that come through from those platforms we call a clue. And that object model has one design principle. That data could be, I can tell I've been in Europe enough because I'm no longer saying data. I'm originally from Australia, that's why. All of these come through a clue, and the principle is that this data could be right or it could be wrong. So we have to go through these many processing steps to figure out some type of insights from this. So this would be a classic record or an example of a record that we would receive from a system. It's not very sophisticated, but essentially you've got names, first name, nicknames, last name. There's not a lot of information there. Now, if you fast forward back 2 years, the way that we solved this in the data integration space was a rules engine. If a person's name is either the same or with some type of distance algorithm or correction algorithm to cater for things like spelling mistakes, or the names are in reverse order, if they were the same and this person's date of birth was the same and their job title was the same, we would give them a weighting. They're probably 77% the same person. You can obviously imagine this is hugely error-prone. And this is where machine learning becomes really handy. So, like some of the speakers before, we started off by using a random forest clustering algorithm to flip this on its head. So instead of us dictating these rules, we in fact completely removed our rules engine, and instead we fed this clustering algorithm with a whole bunch of training data that we had merged in the past, i.e. labeled, and a whole bunch of data that we definitely do not want to merge, okay? Now the attributes, they change per type. So for something like person, some interesting things that we found, obviously you would get rid of attributes like emails and very personally identifying things. What we're looking for is much more fuzzy features. like I alluded to before, i.e. they live in the same location, they've got the same date of birth, it's relatively fuzzy. These are the types of features that you need to feed into a system like this to get the best results. So for example, with people, we went with 24 features that we chose. And it goes without saying that social accounts and aliases of people, i.e. my name's Tim, but it's really Timothy. So aliases of people were where we got the biggest precision gains when we used those as the features that we fed into this random forest. So now that we know about the entity merging, where pattern matching becomes interesting is that once we go into a merge operation, i.e. once the processes before combined with that random forest technique, once it has figured out that it's statistically confident that yes, this should be merged. We use a function called Pearson's chi-square, which is a statistical confidence algorithm where we set the thresholds to 95%, i.e. our decision engine needs to be 95% correct or sure and statistically confident, which means there has to be some range between all the different variations for it to be an answer. Once this has triggered, we then feed this into the graph database. So this is what a Neo4j data structure looks like. Essentially what we do, this is the CEO of Neo4j here. If we are going to do a merge operation on the blue arrow and the green arrow, essentially what we do is we store an array of all the connections that we have to those individuals. These are the kind of things that we can use in the future to say, okay, well, if I'm not sure that we should do a merge, could the graph and the relationships that sit between data help us out in figuring out just that last final piece of the puzzle? I'll give you a classic example. If you see John Smith working on a lot of documents around the EU regulations, and you see Johnny Smith working on a lot of content around the EU regulations, this is the kind of thing that these graph pattern matching would help with in Neo4j. I'm going to skip that one. And I've already given away the surprise. So then on to the unsupervised technique. Now, what we found was that, in fact, we didn't get that much of a precision gain from this. And in fact, in some cases, for some of our customers, it got worse. Once again, welcome to machine learning. What we decided to try out was a neural network approach. And for us, the biggest problem was actually figuring out our parameters. You know, what were our activation functions? And it's not like, when you're dealing with neural networks, you have to vectorize this. So of course, we have to go through this process of vectorizing some text. So we use a classic library that I'm sure most people use here called Word2Vec. What it does, and this is where we gained the biggest precision using a neural net, was that when we're trying to figure out if two people are related or if there's some inference between them, what we did is the parameters that we ended up going with that gave us this huge precision were distance algorithms. I.e., if you went through every single property on John Smith and Johnny Smith, let's take the name, right? What we would calculate is 3 types of distance algorithms. These were the parameters that we would feed into our neural network. And in fact, the neural network we went with in the end was a recurrent neural network. It's slightly better at, because you can imagine data's always flowing in at all time. The ability for us to have some context around time, right, to be able to back propagate to data we have seen in the past allowed us to get this kind of huge gain. And so Soundson dice coefficient and the Levenstein and the Tversky index, they're all good at finding similarity functions or distances between strings typically. Some are better at finding it between hashes. Some are better at finding it between raw strings themselves. I have 5 seconds left. So if you would like to try it out, you can visit us at cluedin.com and /API and request an API key. It's completely free. There's a trial mode that you can just throw data in and have it play with it. So thanks a lot, guys.